balancing of our basket by choosing individual goods CGI, subject to the fact that we have a budget for our total expenditures. So we write the Lagrangian, it's a constrained optimization problem. And lambda t is our Lagrange multiplier. All right, so we take the derivative with respect to CGI. We had the important thing to remember. We did this together was outer derivative and inner derivative with this integral part, and then we can rearrange this to get then that relative demand function. The relative demand function depends on the relative price, with the magnitude of that relative price effect being governed by epsilon, this elasticity of substitution. Okay. Now, I'm going to back out ZT, our total expenditures. Once you put that relative demand function in, for any good I, you can bring the J's out, it's independent of that, and we get then here.
Oh, sorry, I missing the power of PTJ power epsilon. PTJ power, PTJ.
Here.
Yeah,
Right?
yeah, yeah,
And here.
yeah.
You can do the power
Epsilon.
of epsilon.
Yeah. Yeah.
Yeah. Okay, and then it's there again, okay. Right, and we substitute this then back into the aggregator. Right, we see we have our price level, the Z, and then something that's then related to our price level, that's just our price level, the power of 1 minus epsilon. We can do some canceling out of things here, and we get them at ZT, or CT is equal to ZT times the inverse of PT, or we get an expression for ZT. Right, and you get that the shadow price of one more unit of the index, that's another way to interpret lambda, is exactly as PT. Fantastic. Let's see the way I did this. All right, so I start off the exact same way, get the exact relative demand function. I plug into the expenditure constraint, just like you didn't. I have then an expression for CTJ, just like that. Right, now plug this back into the consumption index. That's what you did here, and I get this relationship ZT equals CT, DT, just like you did there. Right, now, what I did, right, you can now use this to relate go from the relative demand to this between two goods to relative to the aggregates. And then once you have that, right, you can replace this here. Rearrange the expression we had in lambda back here. And then rearrange plug this into the consumption index, and we get then that it's equal to, and it's the inverse. Yeah? So it's the how do we interpret this? So we have the shadow price of consumption. So the shadow, I don't know, so you do the shadow price, I'm going to write the shadow value, yeah? Which is why those are just inversely related. Yeah? So our Lagrange multiplier is not the shadow price, it's the shadow value. So the question, that was my mistake. So this is, you answered the problem that I wrote down, and I answered the problem that I not to write down. So the next question wants us to derive this first order condition of the firm's profit maximization part. So we have the optimization problem, the maximization problem on the slides, and we have the answer that we need to get to. So we just have to figure out how to get there, and then we're supposed to log linearize. So we have the objective function for our firms, this discounted future sum of profits, and we're going to be choosing a price PT star. We have our revenue, then we have our nominal total costs at each period at t plus k, conditional on us choosing and being stuck with the price that we choose period t. We take this demand function, right, that we can see here. Right. The relative demand function, yeah. But it's there. Hidden in there. And our stochastic discount factor from the Hausdorff's problem as such. So, right, if you recall the way we solved this problem without nominal rigidities, right? We took the derivative, we plugged in the demand function, and then we took the derivative with respect to the price, and we had these a lot of these terms like revenue and the relative demand we're able to cancel out. It's not going to be quite as easy here. Right, when we took the derivative, we substituted in. We essentially just did the standard bringing the exponent down and leaving it here. But we had a lot of terms like this YTI that we were able to cancel out. It's going to be a little bit more difficult because when we take our derivative, we're not going to have this term just for t. We're going to have this for t plus 1, for t plus 2, and for t plus 3. So we're going to have a bunch of different y's. We're not going to be able to divide through and get rid of one of these i's. But we will be able to do something similar. We're going to be able to factor it out and pull it out front. And that's going to be helpful. All right, so we substitute in the demand functions like before, and now when we take the derivative, all right, we just pull that 1 minus epsilon down, subtract 1 from the exponent, our outer derivative and our inner derivative. Right, this term here is this demand at period t plus k with our price issues at period t. And here we have, again, this yt plus kt, the price. What we did before was we were going to cancel out the yt on both terms here, but we have a sum here. Right, the first term is yt, given t, then yt plus 1, then yt plus 2. So we can't cancel it out. What we can do, though, is we're going to be able to cancel out maybe this constant, 1 minus epsilon, Right, we can bring it over one side because this is in every term of the sum. Right, so let's first bring one half of the sum on one side and one half on the other side of the equality. So work, it's a little bit easier for me to see that way. And then we want to divide through by this 1 minus epsilon. And then right, and what we can do, we can't factor out the yt plus k, but we can multiply both sides with pt star. Why can we do that? Because we have a yt plus k, which is yt plus 0, plus 1, plus 2, plus 3, plus 4. There's a different yt plus k in all of these. The whole point, however, is that we're choosing that one price that's going to be there in every single profit function, right? We're choosing the price that we'd be stuck with. So it's the same pt star for all k equals 0 to infinity. So we can multiply both sides through with this pt star. And then we can bring this minus down here, bring this back to the other side, and we get the first order condition on this slide. And right, if we didn't have this summing, if we weren't stuck with it, we wouldn't have to deal with this discounting, and then we could also cancel out the level of the revenue. And the point here, the reason why these two terms are here, we've gone through this a couple times, right? We're discounting with the probability that we'll even be stuck with this price k periods in the future. We're then also discounting by our owners, the household's valuation of the profits in the future. Here we have the period, look at this, per unit profit. You know? We have, no, it's the, how to define, so we have, it's the per unit mistake. If we were to choose our price optimally in every single period, we would set this equal to 0 in every single period. But we're choosing one price that has to be good for a lot of different periods. Now we know how to deal with periods that are further in the future or further in the present. That's this discounting. In the Q2 we also have correlation, so profits are then missed profits. That's what this is. Think of this as missed not missed profits because it can be also negative. It's just a mistake. This correlation, so this, the mistake turns out to translates to missed profits either way, whether it's too high a price or too low a price. Are we missing out on a lot of profits when our household needs money, or are we just missing out on profits when our household has a lot of money? That's going to be differently valuable to the household. But now we also have this term yt plus k t in there, and the reason why this is important is this gives us the per unit mistake. So imagine what's worse, to make a $1 million mistake on a price, your price is off by $1 million, or your price is off by $10,000. Which is worse? It's hard to say. What we're saying here is that, well, if you only sell one good, one unit, one item, right, then your total mistake was $1 million, which is a lot. But if you have a 10,000 per unit mistake and you sold maybe 1,000 units, oh, that's then 10,000 is then 100,000. 1 million would be 100 times that. 1,000 would be 10 million. So then the total mistake is 10 million. So this is the per unit mistake. You multiply it with the number of units you sell, which gives you the total size of this. And the reason here is that sometimes when you make mistakes, right, if my price is too low, I'm going to make a mistake, but I'm going to be selling fewer goods. So the per unit mistake, right, is going to be smaller. If my price is too, if my price is too high, then I'll be selling fewer units. If my price is too low, then I'll be selling a lot more units. So a price mistake in the upper direction
is going to have a different effect because it's going to reduce the total number of units I sell. So for the same deviation in prices in one direction or the other, you're going to have a different total amount of mistake. And we can rearrange this a little bit. We can define a new variable as our marginal cost. And our markup, right, so we have here the easiest setup. We have the price that we choose. We're trying to set our price equal to this markup over nominal marginal cost. This is the ideal flexible price that we would hit every single period, but we can't until we're going to get it somewhere in between. We're going to try to thread the needle between all of these. Think of it ideally optimal period prices, and this one size fits all PT star for all periods from now on. Okay. Now we're supposed. Yeah.
Can I ask, like, do we have these kind of like math derivation exercise in the exam?
So all right, we'll get to the exam in a couple of days, but I think what you should think of, so yes and no. No? Right? Think of it like, if you were to sit down and do this, I would recommend you practice this. And so now, in terms of an exam question, we have to keep in mind, you have a limited amount of time for an exam question. So sort of like the size of the derivation has to be consistent with that. And it doesn't make sense, I don't think it makes sense to post an exam where you ask like one question that takes you 90 minutes or 60 minutes to derive the answer to if you've practiced and if you're fast, and otherwise you don't pass the exam. I don't think that makes any sense. So, even like, if you just look at it took a while simply to write this down, on the board, and you actually have to do the work first beforehand. So think of this in terms of exam. What's probably going to happen? It's quantitative. We're going to be doing some math. We're doing math together. We're going to test you on the math, but the size of these derivations, are not going to be as big as they are here. The idea is here we're going to give you completeness. So after this class, right? Okay, and then you take the exam. All right, it's good. And then a couple months from now, maybe you're thinking about writing a master's thesis with me, or maybe with Professor Binda, or someone else. And I want to do something with the new Keynesian model, right? Now you don't have the exam setting where you have 60 minutes to do the derivation. You can do things at your own pace, which you need to with your master's thesis. But here we're going to have all the derivations. I think it's useful to have seen sort of step by step how you go through it. And when you go back to like a thesis or paper and you change something, right, then you can see step by step. But just looking at this, just writing this down. So there's a reason why I put this on the slide, because if I were to stand up on the board and just writing this down would take a long period of time. So does that kind of answer your question?
Yeah.
And I'm gonna put up a practice exam that we're gonna talk about on Friday. So that you can have like a better idea, because you don't want to go blind into the exam. That's frightening. I understand that.
Professor, can I ask because we have done some kind of method revisions like this in previous macroeconomic courses as well, and I started to realize that I need to remember certain things, because I cannot rewrite everything and do all of the work that has been done for decades.
Yeah.
So can you show us some kind of scenarios? For example, this is the one for sticky price, right? So we also maybe have another version for flexible prices, and when we change one of the setting, and then we can start with a whole new result at the end, right?
I'm not quite sure I understand. So
we're doing a very specific case, right? We have assumptions about something. So this one is just about sticky prices, right?
Yeah.
So we also are there any other assumptions for this model at this time?
So here we're doing Yeah, we have price setting under this time-dependent price stickiness. We talked about maybe state dependence, and maybe this problem would be different if this lambda depended on the state, right? Then it would be somehow a variable in here, for example. We work together if we don't have sticky prices. So if theta, I just said lambda, I meant theta. If theta is equal to 0, then it's the problem that we did on the board, or that I did on the board in the lecture. That would be the flexible price optimal situation. And it's a markup over marginal cost. This is something that you would see in any micro class. Now, we get that this markup is a constant, and due to these parameters, that's a specific function or a specific result that comes from the assumption of this aggregator function, this basket that has a constant elasticity of substitution between goods, right? If you were to write that more generally, that'd be a little bit more onerous, but it's a good question. Here I've written in such a way that the stochastic discount factor can be different. So this, if you have a different utility function for your household, you're going to derive a different Q. So this is then written pretty generally. Right? We have in our slides that we figure out, we have this? Yeah. For our model, we get this as our stochastic discount factor, but there are other utility functions that might look different. And you would then derive a different stochastic discount factor, and then when you go forward, you would just plug that in here. So kind of, okay. All right, so to get this optimal price setting equation that we had on the slides by log linearizing, now come back to your point. So here I've written that if we have the markup as a right, it's some arbitrary function, it's going to be some function of some time t, then that could be like more general to settings with all sorts of exotic aggregators or ways to put things together. You know? Here it's constant, and if you go back to the slide before, right, the fact that it's related to this one parameter epsilon is due to our specific Dixit-Stiglitz assumption. And it's a specific assumption, but most people make that assumption. So it's kind of, it's specific, but general in the sense that that's what people do most of the time. There are Kimball aggregators, some, yeah. But for us, this is a good enough place to start. Yeah, I think so. I was at this question. This is my. I asked Uwe Hassler this because he teaches economics and statistics, econometrics and statistics. I don't think I understood frequentist statistics really until I did my PhD. The reason is it's hard to explain frequentist statistics intuitively. Like if you think of a confidence interval, so you estimate a parameter and you have a confidence interval. What does this confidence interval mean? Right? When you first explain to the students, so the first semester of the bachelor's course, you would tell them something like, so if I have the 90% confidence interval means that I have 90% confidence that the parameter is in this interval, right? Which is not at all what a confidence interval means in frequentist statistics, right? It tells me that with my model, so with this sample size, if I were to draw another sample the same size from this model, and do that many times, 90% of the confidence intervals that I would then calculate would contain this parameter. Right? So, what does that even mean? You don't understand statistics. I want to know, I've estimated this parameter, I want to know how this is related to the true parameter. And there's no such thing in frequentist statistics. So this is it's extremely confusing to explain it to bachelor students. And so what we end up explaining it is by using Bayesian statistics. In Bayesian statistics, you have a posterior credible set, which means I've estimated a parameter, and based on the priors that I had and the data that I've now seen, I assign 90% probability that the true parameter lies in this range. This makes intuitive sense, and this is the way we understand things. But we teach our students first frequentist statistics, where it's difficult to interpret this confidence interval, the related object. And so it's always and I have a lot of sympathy sort of for this, when you start going through these models, we're going through another model, this model, that model, this class, and a similar model, and similar, it's kind of a lot to take in. And the whole point is that as you're working through these different models, different ways of deriving things with different teachers, different professors, after a while, it's all going to start to settle, the pieces will come together. Right? So don't be worried or discouraged, I guess is what I'm saying. It's that you're in your master's degree, and this is a point in time where you appreciate. Okay, your bachelor's, you just learn what you're told, and then that's the answer. Right? And now you're a master's student, so you're kind of in a position where you know enough to know how little you know, right? Which is always, and you get to the point where I am, and I learn more every day of things that I don't know, then I learn new things. So my ignorance, or my awareness of my ignorance, right? It's never stopped. For my master's degree, it still grows more quickly than my knowledge. Yeah? But it's something I have gotten used to. Yeah? And that's okay. And you're still getting used to the fact that, wait a second, this is a lot of different things. There's not one answer. What's the one answer I need to know? How do I, right? What's the answer I need to know for life, or for my job, or for the degree, or for the exam? It's hard to say, right? It's always different pieces. I mean, you can kind of put some of the pieces together. We've spent a bunch of days with like ISLM sort of stuff. We're doing some days with ESGE. I bet there's going to be a mix of that kind of on the exam. Yeah? Some things have been graphical and intuitive. Some things have been mathematical. Yeah, I bet there's going to be a mix of those two things. Maybe in the past week and a half you've gotten to know me a little bit, and maybe you think, So Professor Mayagouda has, we're doing lots of things, so he has, high expectations, but he's also, it seems to be a pretty fair person who's trying to make this approachable. So I bet the exam isn't going to be the, do this one derivation from memory, otherwise you fail, but it's probably going to be something that's a little more doable or approachable. Hopefully, is what I'm trying to do. Yeah? So that's sort of, we'll look at the exam, think about the exam specifically in a couple of days. So when we log linearize this, let's just rearrange things a little bit. Divide through by last period's price level, so we get this optimal price adjustment. And this can relate, we can then relate this to our real marginal cost and its inflation. So we're going to approximate around a steady state, so we'll call what the steady state is. In a steady state, the inflation is 0, so this gross inflation rate is 1, which means all prices are the same. So this is equal to 1, this is equal to 1. All firms, the prices are the same. All firms have the same price, which means all vintages of prices are the same. So all firms are always going to be producing the same amount. Output is the same. So then also then here, we're going to have marginal costs are going to be the same for all firms. All firms have the same marginal costs, and they're going to be constant as well, because we're producing a constant amount and prices are constant. Prices are constant, production is constant. Production only goes towards consumption, so consumption is also constant. Then our stochastic discount factor between any two periods is simply the amount of impatience we have over that time horizon. Okay. It's useful to
to split this equation up, put one half on one side and one half on the other side.
Can you get back to the previous slide?
Yeah.
Like normally we already know that the phi one, the little phi one is already like the marginal cost, and that is the nominal one. The little, yeah.
Yes, we define this as our marginal cost.
Yeah. So that is the nominal one because like when
Yeah,
you-
it's nominal.
Okay. So how can we interpret like the real marginal cost, like in what kind of unit?
So think the real marginal cost would be, it's the cost in terms of the good of producing another unit of the good. And so a standard way of thinking about the real marginal cost, or real cost would be how many hours of labor input, right? So think of, if I want to produce one good, I need so many hours of labor, and I need so many, I don't know, tons of steel and gallons of gasoline. Those are all real objects that go in. We've just sort of normalized it, so think of then, you know, the unit of labor is worth 1 unit of the good, a ton of steel is 2 units of the good, right? So it's all expressed in terms of units of the good.
Okay.
Okay. And so this expression here in the steady state, right, we're going to then get the relationship that log inflation, log nominal marginal cost. Right, these QTs are on both sides, so we cancel out. These theta Ks are on both sides. The steady state they cancel out. So this equation implies relationship here at the bottom, steady state. And so now the way we're going to log linearize this is let's first write everything in terms of the exponential. All right, so this is also a neat trick. Instead of writing the stochastic discount factor, we're going to write e to the power of the log of the stochastic discount factor. That's the same thing, it's just more complicated this way. No. Right? It's going to make our life easier in a minute. No? So we have everything, right, because now you can already see this. We've taken this multiplicative thing, and it's the additivity to the logarithm is up here. No? And so we're just going to approximate this exponential function to get where we need to go. No? Right, so let's take then the left-hand side and approximate this. So we're going to have, right, it's a sum with lots of different, with an infinite sum of these exponential expressions on the left-hand side, and we're going to approximate them at a point, and then the slope and the deviations. All right, so we get then at the point, this is the steady state, and the fantastic thing about our exponential function is that it is its own derivative. Right, so our slope is also equal to this exact same term times then the individual deviations in our variables here, our log deviations. The same thing on the right-hand side. We have the point, and we have the slope times and the sum of all their deviations. We can now start to reduce this, right? We can use these steady state relationships to simplify this a little bit, pull out this q to the power of k, right? This is simply beta to the power of k. Pull this beta k out in front here, this theta k, and we have still the point, the slope, and the deviation of these variables, right, from their steady states. And the same on the right-hand side too. Now these steady states are going to drop out. This is where they're defined. This term is equal to this term. So we had here. Right, and then we do the, all right, yeah, then we, the separation here. Then we do the standard approximation. We have that e to the x is the same, approximately the same as 1 plus x for a small x. So we've now replaced wait, no. We did that. What is this? We already did the approximation for localization. We have, we can rewrite both of these terms as the same as those terms, divide through on both sides, and we get 1 plus this is equal to 1 plus this. Yeah, that's what we have there. And now we see we have these 1s on both sides. It's the same expression here, with the same weights and the stochastic discount factor up front, and these conditional future outputs. So we have then here that this weighted sum of, oh wait, and these of course don't change, so it's just a sum some weights. It's a geometric series out in front of our price adjustment is equal to, and here we have some sort of infinite sum of these current and future marginal costs. We can resolve this geometric series. Right, since pt and pt minus 1 don't have any k, we can bring them out front, and then this is simply 1 over 1 minus beta theta, multiply that on both sides, and we get, this is that the first expression in the lecture slides, and this is the second one. If we write this instead of the deviation of marginal costs, we're not, nominal marginal cost, if we write this as the log of nominal marginal cost. Right, so this is also a good example. Doing this derivation in an exam would be mean, I think. Now, what we can do in an exam, we've done a lot of log minimization. I've given the opportunity of showing you many different ways. So some form of log minimization might be something that comes up in the exam. But log linearizing, this equation is probably a little too much. But maybe part of it, or showing this or that, or interpret this, there's some things we can do. Okay. So let's take a 10-minute break, and we will come back to the rest of the problem set. We look at real marginal costs. Interpretation of the Keynesian model. So it's solving forward, interpreting this, and solutions and some interpretations. So we're gonna be experts doing problems of the Keynesian model by the end of the day. So 10-minute break. Do we need to charge this up or the power?